Welcome back to The Explainer. Today, we're diving into a genuinely fascinating engineering triumph. Have you ever wondered how complex, high-speed transportation networks manage to maintain such incredibly near-perfect safety records? Well, spoiler alert, it is absolutely not about luck. And it's not just about having well-trained staff either. We're talking about systematic implementation. It's this rigid, multi-layered architecture of defense that's constantly operating, completely invisibly, in the background of literally every single journey you take.
So, to get us started, I want to throw a question your way. Who really stops a train? I mean, seriously, think about it for a second. We're dealing with thousands of tons of steel hurtling down a track. A typical freight train going, say, 55 miles per hour, that beast can take over a mile to come to a complete stop. Now, it's super easy to just assume the driver sitting up in the cab is the one who stops it, right? But safety in these extreme environments isn't just about good driving. It's about a highly structured, overlapping system that was designed from the ground up to eliminate human error entirely.
Here's our roadmap for today's deep dive. We'll start with the human error problem, move on to interlocking as the primary safety layer, then look at how we actually prove commands are safe. After that, we'll cover guarding against driver mistakes and wrap it all up with automatic train protection systems.
All right, Section 1, the human error problem. Let's look at why automated safety is an absolute must. So why do we even need all these invisible safety layers in the first place? Well, honestly, it comes down to the inherent vulnerabilities of us humans, right? No matter how incredibly well-trained a driver or a signaler might be, people make mistakes. It happens. A driver might misjudge braking distance in a heavy downpour, they might get hit with fatigue, or even face a sudden, unexpected medical issue. And all of that can lead to the absolute ultimate railway nightmare, passing a signal at danger, otherwise known as a SPAD. Because human operation inherently carries these risks, the overarching control system itself literally has to take final absolute responsibility. It can't just trust the human, it absolutely has to verify and enforce the rules.
Moving on to Section 2, Interlocking, which acts as our primary safety layer.
Okay, so how do we actually enforce safety at the infrastructure level? Enter our first major line of defense, the interlocking. At its core, an interlocking is a feature of a control system that makes the state of two different functions mutually dependent. I like to think of it as a strict, totally unyielding digital bouncer. It's a logic gate that blindly checks all the predefined rules of the railway and flat out refuses to allow any unsafe actions. Period. If a signaler tries to route a train onto a track that's already occupied, the interlocking simply says, nope, not happening. It prevents conflicting movements before they can even begin.
Now picture the interlocking sitting right smack in the middle of the whole operation. Up at the top, you've got the human operators in the control center making requests. And down at the bottom, you have the physical trackside equipment. You know, the points, the signals, the train detection systems. The interlocking acts as this impenetrable safety hub right between human intent and physical reality. Its whole job is to ensure that a human mistake made in the control room absolutely never makes it out to the physical tracks.
Section 3. Let's look at proving commands are safe and see how this logic actually plays out. So how does our digital bouncer actually make these critical decisions? Well, it relies on a very strict step-by-step command sequence. First, an operator requests a route, but the interlocking doesn't just blindly wave that request through. Instead, it checks the real-time current state of the railway. It asks, where exactly are all the trains right now? Are the points properly locked? The system mathematically verifies the operator's request against what's physically happening outside. The command is only executed and sent to the trackside equipment if the path is proven to be definitively, undeniably clear. Because this interlocking layer is the ultimate arbiter of safety, it's held to some insanely rigorous standards. Modern interlockings have to meet what's called Safety Integrity Level 4, or SIL 4. Guys, that is literally the highest possible safety rating for an industrial control system. It basically means the probability of an unsafe failure is practically zero. Plus, it operates on a foundational fail-safe principle. We all know that in engineering things break. Wires get cut, power grids fail, but if this system experiences a fault or loses its communication links, it's physically and electronically designed to immediately revert to a safe state. And in railway terms, the safest state, everything stopped. Any failure automatically drops all surrounding signals to red, danger, bringing all trains to a halt until the issue is fixed.
Which brings us to Section 4, Guarding Against Driver Mistakes.
Now this brings up a pretty critical question. What happens if the interlocking does its job perfectly, but the driver in the cab ignores the red signal, or, heaven forbid, falls asleep at the controls? This perfectly illustrates the beauty of a layered defense strategy. We never just rely on one single safety net. While the interlocking forms that primary safety layer, checking the control room and the tracks, we have a vital secondary layer called train protection. And its entire reason for existing is to sit right there in the cab and supervise the driver.
Just imagine for a second that you're sitting in the driver's seat, looking out the front window, and you are blasting along at over 100 miles per hour. At those kinds of speeds, a trackside signal literally flashes by in a fraction of a second. Human reaction times just aren't always fast enough to process a sudden restriction and manually yank the heavy braking required. We just can't rely solely on the human eye and a manual brake handle anymore. And that is exactly where automated backup systems step in to take control when the human driver simply can't.
And finally, Section 5, Automatic Train Protection Systems.
Let's really dig into how these secondary layers actually supervise the train's movements in real time. There are generally two main approaches here: automatic train protection, or ATP, and the train protection warning system, or TPWS. Now, ATP is basically the gold standard. It gives you full continuous supervision. It constantly calculates a safe braking curve, and if the driver goes even slightly too fast, boom, it steps in. TPWS, on the other hand, is more intermittent. Think of it as using trackside loops that act kind of like speed traps at known high-risk locations. If a train approaches a red signal going faster than 75 miles per hour, TPWS realizes, uh-oh, this train definitely won't be able to stop in time, and it forcefully takes over.
So the ultimate takeaway here is active intervention. These systems don't just beep and sound a warning alarm, they physically take action. If a driver fails to obey a signal or blows past the safe speed limit, these systems act as a hard fail-safe. They completely remove the human element during a critical failure, and they automatically slam on the emergency brakes to stop the train before a collision can even happen. It is literally technology stepping in to save lives when human capability reaches its absolute limit.
As we wrap up and look back at these incredible engineering achievements, from those interlocking digital bouncers in the control rooms to the automated braking systems riding shotgun with the drivers, it leaves us with a pretty provocative question. How might these invisible, overlapping layers of automated logic and mechanical failsafes be applied to the future of all human transportation? I mean, as we move closer and closer to self-driving cars and fully automated airspace, the railway's philosophy of systematic, fail-safe implementation isn't just some cool bit of history. It might actually be the exact blueprint we need for the future. Thanks for joining me on this explainer, and keep questioning how the systems around you really work.